Hey guys, welcome back to Simple Science, where today we're going to be going over Unit 6 of AP Chem, which is all about thermodynamics. Thermodynamics is the study of heat transfer in chemical reactions and different types of processes. And to start learning about thermodynamics, we first need to go over some basic terms. In chemical reactions, there's a system, and there are the surroundings. The system is where the reaction itself is taking place, and the surroundings is the area around it. In some reactions, heat energy gets transferred from the surroundings and into the system. This means that the system absorbs heat from the surroundings. These type of reactions are called endothermic. In an endothermic reaction, the surrounding area will start to cool down because heat from the surroundings is being absorbed by the system. Now, in another type of chemical reaction, heat is released by the system into the surroundings. This is called an exothermic reaction. In an exothermic reaction, the surroundings start to feel warm because heat energy is going into the surroundings. Another concept you'll need to understand is enthalpy. Enthalpy is a type of thermal energy, and it's the heat required to break or form bonds in a substance. In chemistry, enthalpy is represented by the letter H. In chemical reactions, a change in enthalpy, or delta H, represents a change in the amount of energy from the reactants to the products. Because endothermic reactions absorb energy from the surroundings, the products of an endothermic reaction will gain energy. This gives endothermic reactions an increase in enthalpy, or a positive delta H. On the other hand, exothermic reactions release energy into the surroundings, so the products of the reaction lose energy. This gives exothermic reactions a decrease in enthalpy, or a negative delta H. The change in energy during a reaction can be represented by a potential energy graph. Let's look at an example of one of these. This is an example of a potential energy graph for an endothermic reaction. On the x-axis, we have time, which shows how the reaction progresses. And on the y-axis, we have potential energy, which is measured in a unit called joules. Potential energy is the stored energy between atoms. Now, first, let's look at the potential energy of the reactants, which is represented by this line near the beginning. Now, this is the potential energy of the products, which is this line near the end. As you can see, the products have a higher potential energy than the reactants because in an endothermic reaction, enthalpy increases. The distance between the potential energy of the products and the reactants represents delta H, or the change in enthalpy. In this case, delta H is positive 42 joules, since the energy of the products is 169 joules, and the energy of the reactants is 127. The difference between those is 42. But what about this little hump over here? That hump is the activation energy of the reaction, which is the amount of energy required for the reactants to form the products. Now let's look at a potential energy graph for an exothermic reaction. Here is the potential energy of the reactants, and here's the potential energy of the products. The potential energy of the products is lower than the reactants because exothermic reactions have a decrease in enthalpy because energy is released into the surroundings. The difference between the reactants and products' potential energy is delta H, just like we discussed earlier. And again, this hump represents the activation energy. And just like we said earlier, the activation energy is the minimum amount of energy needed for the reactants to become the products. Now, how do we tell if a process is endothermic or exothermic? Well, breaking bonds requires energy from the surroundings, so processes like melting and vaporization are endothermic because bonds between molecules are being broken. In melting, bonds between water molecules in their solid form are broken to make liquid water molecules, a process that requires energy. This makes it an endothermic process. In vaporization, hydrogen bonds between liquid water molecules are broken to convert them into a gas, which is also endothermic. On the other hand, when bonds are formed, energy is released, so processes like freezing and condensation are exothermic. Now, let's review some of the properties of exothermic and endothermic processes. Exothermic processes, where energy is released into the surroundings, have a decrease in enthalpy, or a negative delta H, and the area surrounding an exothermic reaction feels warmer. Exothermic processes also involve forming bonds. In contrast, endothermic processes, where the system absorbs energy from the surroundings, have an increase in enthalpy or a positive delta H. And the area surrounding an endothermic reaction feels colder. Endothermic processes involve breaking bonds. So, we know about heat transfer, but what's the difference between heat and temperature? We usually think of temperature as the same thing as heat, meaning how hot or cold something is. However, there's a key difference. Temperature is the average kinetic energy of particles, so it measures how fast particles are moving. In chemistry, we usually measure temperature in Kelvin, or K. Meanwhile, heat is the thermal energy that particles transfer to each other. We usually measure heat, and really any kind of energy, in joules. Particles that move faster on average will have a higher temperature. Meanwhile, particles that move slower on average will have a lower temperature. So now that we know the difference between heat and temperature, I'm going to pose a hypothetical question. Let's say you have a pot of boiling water that you just took off the stove, and you leave it in the kitchen at room temperature. What's going to happen to the temperature of both the room and the water? Well, you probably know that the water's going to get colder, and the air around it is going to get warmer, until both of them reach roughly the same temperature. This concept of heat exchange is called thermal equilibrium. In this case, thermal equilibrium happens because the water molecules will collide with the air molecules and transfer some of their kinetic energy until both of them are at the same temperature. One way you can measure heat transfer is with calorimetry. In calorimetry, you use a calorimeter, which is a styrofoam cup with a lid, some water, and a hole for a thermometer. First, you measure the initial temperature of the water. You then take a heated substance, usually a block of some metal, and drop it into the calorimeter and stir it until it reaches thermal equilibrium. The lid prevents heat from escaping the calorimeter, so all the heat from the block of the metal will only transfer to the water. After it's reached thermal equilibrium, you can measure how much water temperature has changed and then plug that into an equation to measure how much heat the metal lost. The equation used to measure this heat transfer is called Q equals m times C times delta T. Q is the amount of heat lost or gained, and it's usually measured in joules. When heat is lost, Q is negative, and when heat is gained, Q is positive. M is the mass of the material measured in grams. Delta T is the temperature change of the material measured in degrees Celsius. Some problems might give you the temperature in Kelvin, so remember to subtract 273 from the temperature in Kelvin to get it to Celsius. Finally, C is the specific heat capacity of the material. Specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Materials with a higher specific heat capacity will need more energy to heat up to a certain temperature. For example, copper's specific heat capacity is 0.385 joules per gram degree Celsius, and pine wood has a specific heat capacity of 1.2 joules per gram degree Celsius. Assuming you have the same mass of copper and pine wood, to heat them both up to the same temperature, the pine wood would need more heat, since it takes more heat energy to raise its temperature. Similarly, if you were to heat both the pine wood and the copper with the same amount of heat, the pine wood would end up at a lower temperature than the copper, because since the pine wood has a higher specific heat, its temperature changes less with the same amount of heat. When you're doing calorimetry problems, it's important to note that the amount of heat gained by the water is the same amount of heat lost by the other material. So, if you find the heat gained by the water, or the Q for water, you can just flip the Q's sign from positive to negative to get the heat lost by the material and vice versa. If the Q for the water is 50 joules, then the Q for the material in the calorimeter is negative 50 joules. This means that the water gained 50 joules of energy and the other material lost 50 joules of energy. In the same way, if you know the other material's Q is negative 50, then the water's Q is positive 50. Let's practice with an example problem. This problem tells us that a student heats up a block of copper and places it into a calorimeter with 12 grams of water at a temperature of 294 Kelvin. After stirring the calorimeter until it reached thermal equilibrium, the temperature of the water was found to be 300 Kelvin. How much heat in kilojoules was gained by the water? So the specific heat of water is 4.18 joules per gram degree Celsius. Okay, so this problem tells us to solve for the Q, which is the heat gained by water, and it gives us the mass of the water, its specific heat, and both its final and initial temperature. However, the temperatures are given in Kelvin, and the specific heat is given in joules per gram degree Celsius. In order for the units to match, we have to convert the temperature into degrees Celsius. We know from our formula sheet that the temperature in Kelvin minus 273 equals the temperature in Celsius. For our initial temperature, 294 minus 273 gives us 21 degrees Celsius. For our final temperature, 300 minus 273 gives us 27 degrees Celsius. Subtracting our initial from our final temperature, we get a temperature change of 6 degrees Celsius. Now we can plug in our mass of water, which is 12.0 grams, our specific heat, 4.18 joules per gram degree Celsius, and our temperature change, 6 degrees Celsius, into Q equals mc delta T. 12 times 4.18 times 6 gives us 301 joules. However, this answer asks us for the heat gained in kilojoules, and 1 kilojoule is equal to 1,000 joules. So, dividing 301 by 1,000 gives us 0.301 kilojoules of heat gained by the water. Next, this problem tells us that after repeating the experiment, the student realized they made an experimental error, and the water should have absorbed 0.420 kilojoules of heat. The problem asks us to list a type of experimental error the student could have made. So, we know that the student found the water absorbed 0.301 kilojoules, but the water should have absorbed 0.420. This means that the student did something that lowered the calculated value of the heat absorbed. One reason for this could be that the student didn't secure the lid properly on the calorimeter, allowing some of the heat to escape. This would mean that not all of the heat from the copper block was transferred into the water, artificially lowering its final temperature. Then, with this lower final temperature, the student would have calculated a lower value for the heat absorbed by the water. Another possible reason for this could be that the student recorded the mass of the water wrong. If some of the water spilled while recording the mass, the student would have used a lower value for the water's mass in the calculations, leading to a lower value for the amount of heat absorbed by the water. Let's do another example problem. This problem tells us that a 10.0 gram block of silver is heated up and placed in a calorimeter with 31 grams of water, where the temperature of the water was initially 23.0 degrees Celsius. After the system reaches thermal equilibrium, the temperature of the water increases to 29.0 degrees Celsius. Given that the specific heat of water is 4.18 joules per gram degree Celsius, and the specific heat of silver is 0.235 joules per gram degree Celsius, how much did the silver decrease in temperature after reaching thermal equilibrium? So, before solving, let's first see what we know. We have the final and initial temperature of the water, the mass of the water, and the specific heat of the water. This means that we have the delta T, M, and C for the water, which is enough to find Q, or the amount of heat that the water gained. We also have the mass and specific heat of the silver, and we're trying to find its change in temperature, or delta T. Once we find Q for the water, we can flip the sign for Q and use it as the delta T for the silver. First, let's find Q for the water. The final temperature of the water is 29.0 degrees Celsius, and the initial temperature of the water is 23.0 degrees Celsius. Subtracting initial from final gives us the change in temperature, or delta T, which is 6 degrees Celsius. Now we can multiply M, C, and delta T for the water. 31 grams of water times 4.18 joules per gram degree Celsius times 6 degrees Celsius gives us a Q of 777 joules. This means that the water gained 777 joules of heat. Now, to find the Q for the silver, we can flip the sign from positive to negative, giving us negative 777 joules for Q. Plugging Q, M, and C for silver into the equation, we get that negative 777 joules equals 10 grams times 0.235 joules per gram degree Celsius times delta T. Dividing negative 777 by 10 times 0.235 gives us a delta T of negative 331 degrees Celsius. This means that the temperature of the silver decreased by 331 degrees Celsius. That's some cold silver. Next, we're going to be going over heating and cooling curves. These graphs show us how temperature changes when a substance is in its solid, liquid, or gas form. This is an example of a heating curve. On the x-axis, we have the addition of heat, and on the y-axis, we have the change in temperature. On this first sloped part of the graph, the substance is a solid. On the second sloped part, the substance is a liquid, and on the third sloped part, the substance is a gas. So, when it's solid, we know that as you add heat to it, the temperature increases. But what happens when the solid starts melting into a liquid? We can see that even though we're adding heat, the temperature doesn't change. This is because the added heat is used to break the bonds between the solid molecules instead of being used to increase their temperature. And in this part, we start to see the solid melt. This point is called the melting point, and we can see the same thing over here. As the liquid starts heating up, its temperature increases. But when it starts boiling and turning into a gas, the temperature doesn't go up because the heat is used to break the IMFs in the liquid to turn it into a gas. Now, in calculations, when a substance is being melted, we use a value for the enthalpy of fusion, and when a substance is being boiled, we use the enthalpy of vaporization. Enthalpy of fusion is the energy needed to change a substance from a solid to a liquid, and enthalpy of vaporization is the energy you need to change a substance from a liquid to a gas. And both of them are usually recorded in joules per gram. Now, let's try to solve a problem with the heating curve. This problem gives us a heating curve for water and asks us how much heat in joules is required to heat up 5 grams of water from 15 degrees Celsius to 72 degrees Celsius, assuming that the water's enthalpy of fusion is 334 joules per gram, its specific heat as a solid is 2.09 joules per gram degree Celsius, and its specific heat as a liquid is 4.18 joules per gram degree Celsius. So let's look at this heating curve. Negative 15 degrees Celsius is somewhere around here, and 72 degrees Celsius is somewhere around here. So from negative 15 to 0 degrees Celsius, the water is a solid as it's being heated up. Then, once the water reaches 0 degrees Celsius, it starts to melt. And after that, from 0 to 72 degrees Celsius, the water is a liquid as it's being heated up. So, to calculate the heat needed, we need to add up the heat needed to raise the temperature of solid water from negative 15 to 0 degrees, the heat needed to melt the water, and finally, the heat needed to raise liquid water's temperature from 0 to 72 degrees Celsius. First, let's find the heat needed to raise the temperature of ice from negative 15 to 0 degrees Celsius. For this, we can use Q equals mc delta T. The mass of the water is given as 5.0 grams, and its specific heat capacity is given as 2.09 joules per gram degree Celsius, because we're heating up solid ice. And our temperature change is 15 degrees Celsius, because the final temperature, 0, minus the initial temperature, negative 15, gives us positive 15. 5 times 4.18 times 15 gives us 157 joules of heat. Now, let's find the heat needed to melt the water. For this, we take the heat of fusion, which is 334 joules per gram, and multiply it by the mass, which is 5.0 grams. 334 times 5 gives us 1670 joules. Next, let's find the heat needed to raise the temperature of liquid water from 0 degrees Celsius to 72 degrees Celsius. Because this is heating when increasing the temperature, we're going to use Q equals mc delta T again. Our mass is 5.00 grams, our specific heat is 4.18 joules per gram degree Celsius, and our temperature change is 72 degrees Celsius. 5.00 times 4.18 times 72 gives us 1,505 joules of heat needed. Finally, let's add up the heat that we've calculated so far. 157 plus 1670 plus 1505 gives us a total of 3,332 joules of heat, rounded to 4 sig figs. This is another problem with the heating curve, this time for methanol, and it asks us how many kilojoules of heat need to be removed to cool down 4.2 grams of methanol from 83 degrees Celsius to negative 104 degrees Celsius. Assuming that its enthalpy of fusion is 107 joules per gram, its enthalpy of vaporization is 826 joules per gram, its liquid-specific heat is 2.44 joules per gram degrees Celsius, its gaseous-specific heat is 1.43 joules per gram degrees Celsius, and its solid-specific heat is 0.97 joules per gram degrees Celsius. So let's put these values on a heating curve. 83 degrees Celsius is right around here, and negative 104 degrees Celsius is right around here. To cool it down from 83 to negative 104, we first need to cool down the ethanol to its boiling point, which is 64 degrees Celsius. Then, methanol needs to condense into a liquid. After that, it needs to be cooled down from 64 degrees Celsius to negative 97.7 degrees Celsius. And then after that, it needs to freeze. Finally, it needs to cool down from negative 97.7 to negative 104 degrees Celsius. With all these steps, it looks like that we've got our work cut out for us. First, let's calculate the heat lost when cooling down from 83 degrees to 64 degrees. Using Q equals mc delta T. The mass is 4.2 grams and the specific heat as a gas is given as 1.43 joules per gram degree Celsius. For delta T, we subtract our initial temperature, 83 degrees Celsius, from our final temperature, which is 64 degrees Celsius, giving us a delta T of negative 19 degrees Celsius. 4.2 times 1.43 times negative 19 is negative 114 joules. Now, let's find the energy needed to condense ethanol from a gas to a liquid. Its enthalpy of vaporization is given to us as 826 joules per gram, and its mass is given to us as 4.2 grams. But because we're doing the opposite of vaporization, which is condensation, we need to turn 826 into negative 826. Negative 826 times 4.2 gives us negative 3,469 joules. Next, we'll find the amount of heat needed to cool down methanol at 64 degrees Celsius to negative 97.7 degrees Celsius, which is its melting point. And because this is a temperature change, we're going to use Q equals mc delta T. For delta T, let's subtract the initial temperature, 64, from the final temperature, negative 97.7. This gives us a delta T of negative 162 degrees Celsius. 4.2 grams times 2.44 joules per gram degree Celsius times negative 162 degrees Celsius gives us negative 1,660 joules. Now, let's find the amount of heat needed for ethanol to freeze. The heat of fusion is given as 107 joules per gram, and the mass is 4.2 grams. Again, we're going to flip the sign for the fusion since we're doing the opposite of melting, which is freezing. Negative 107 times 4.2 gives us negative 449 joules. Finally, let's find the amount of heat needed to cool down solid methanol from negative 97.7 degrees Celsius to negative 104 degrees Celsius using Q equals mc delta T. To find delta T, we subtract negative 97 from negative 104, giving us a delta T of negative 6.30 degrees Celsius. The mass is 4.2 grams times the solid specific heat of 0.97 joules per gram degree Celsius times negative 6.30. This gives us a total of negative 2,570 joules rounded to 3 sig figs. Now, let's add up all the joules that we have so far. Negative 114 minus 3,469 minus 1,660 minus 449 minus 2,570 gives us a grand total of negative 8,262 joules. This means that 8,262 joules of heat need to be lost for methanol at 83 degrees Celsius to cool down to negative 104 degrees Celsius. Converting that into kilojoules, like the problem asks, we get 8.262 kilojoules. Now, we're going to learn another way to calculate enthalpy, this time with a chemical reaction. As we know, when chemical reactions take place, there's usually some sort of heat transfer going on, whether the reaction absorbs heat from the surroundings or releases heat into the surroundings. We represent the heat that's gained or lost in a reaction with its change in enthalpy, or delta H. In chemical reactions, delta H is shown in kilojoules of heat per mole of reaction. Let's look at an example. Here we have a dissolution equation where calcium nitrate dissolves into 2 moles of NO3- and 1 mole of Ca2+. The delta H for this reaction is negative 18.67 kilojoules. Because it's negative, we know that this dissolution is exothermic, meaning that it releases heat. So, for every 1 mole of the reaction, which means for every mole of calcium nitrate that's dissolved, 18.67 kilojoules of heat are released. Let's try to do a problem with this. The problem tells us that 7.00 grams of LiCl, or lithium chloride, are dissolved into 100.0 grams of water at 21.2 degrees Celsius. After the LiCl fully dissolves, the temperature rises to 22.57 degrees Celsius. The problem then asks us to calculate the enthalpy of solution for LiCl in kilojoules per mole. Assume that the specific heat of the solution is 4.18 joules per gram degree Celsius. So, with the information given, we first need to calculate the amount of joules of heat released with Q equals MCAT. Our total mass for the solution is 107 grams, the specific heat is 4.18 joules per gram degree Celsius, and the temperature change, which is final minus initial, is 1.37 degrees Celsius. 107 times 4.18 times 1.37 gives us roughly 613 joules of heat produced. Since the problem is asking us to calculate for the enthalpy of solution in kilojoules per mole of reaction, we have to divide this number by 1000 to give us 0.613 kilojoules. Now we need to figure out how many moles of LiCl there are, since the problem asks for the enthalpy in kilojoules per mole of reaction. The molar mass of LiCl is 42.39, and you can get that by adding the molar masses of 1 mole of lithium and 1 mole of chloride. And our problem tells us that 7 grams of LiCl were in the solution. 7 divided by 42.39 gives us 0.165 moles of LiCl. Now, to find the enthalpy of solution in kilojoules per mole, we divide 0.613 kilojoules by 0.165 moles of the reaction, giving us an enthalpy of solution of negative 3.72 kilojoules per mole. Now, the reason I flipped the sign is because the temperature of the solution increased. Because of this, we know that the dissolution of LiCl is an exothermic reaction, meaning its enthalpy of solution has to be negative. Another way to calculate enthalpy is with bond energies. You can calculate the enthalpy of a reaction by taking the sum of the enthalpies of all the bonds broken and subtracting the sum of the enthalpies of all the bonds formed. The reason we subtract bonds broken from bonds formed is that forming bonds releases energy and breaking bonds takes energy. So, the enthalpy for bonds broken is going to be positive, and the enthalpy for the bonds formed is going to be negative. In these types of problems, the question will usually give you all the bond energies for the different bonds in a chemical reaction. Let's take a look at an example. This problem gives us a chemical reaction where carbon dioxide and water react to make carbonic acid, or H2CO3, and it gives us the different bond enthalpies on the side. It tells us to find the enthalpy of the reaction using the bond enthalpies that were given. First, to find out how many of each type of bond we actually have, I'm going to draw the Lewis structure for each of these molecules. This is a Lewis structure for CO2, with 2 carbon-oxygen double bonds. This is a Lewis structure for H2O, with 2 hydrogen-oxygen single bonds. Finally, after I tested out a couple of different Lewis structures, I landed on this structure for H2CO3, which has 1 carbon-oxygen double bond, 2 carbon-oxygen single bonds, and 2 oxygen-hydrogen single bond. If you're struggling with drawing a Lewis structure for this, I would try to place the hydrogens in different places to see which gives you the least formal charges on all the atoms. Now we can find the enthalpies for the bonds formed, which are all the bonds in H2CO3. There are 2 OH bonds, and each OH bond has an enthalpy of 463 kilojoules per mole. 2 times 463 is 926 kilojoules. H2CO3 also has 2 carbon-oxygen single bonds. Each CO single bond is 358 kilojoules per mole, and 2 times 358 is 716 kilojoules. Finally, there is 1 CO double bond, which is 799 kilojoules. Now, to get the sum of the enthalpy for all the bonds formed, we add these all together. 799 plus 716 plus 926 gives us 2,441 kilojoules. Now to find the enthalpy of the bonds that were broken. Because CO2 and H2O are the reactants, their bonds between the atoms are going to be broken to form H2CO3. There are 2 CO double bonds in CO2, and each of those is 799 kilojoules. 2 times 799 gives us 1,598 kilojoules. Now, there are 2 HO bonds in H2O, and each has an enthalpy of 463 kilojoules per mole. 2 times 463 gives us a total of 926 kilojoules. Adding the bonds broken together, we get 926 plus 1,598 gives us 2,524 kilojoules. Now, remember, we subtract the bonds formed from the bonds broken. The enthalpies for the bonds broken is 2,524, and the enthalpies for the bonds formed is 2,441. 2,524 minus 2,441 gives us a delta H of 83 kilojoules per mole of reaction. The next way we're going to learn about how to calculate enthalpy of a reaction is using enthalpy of formation. And the enthalpy of formation is the change in heat that occurs when 1 mole of a molecule is formed from its individual elements. For example, this equation gives us the formation of sulfur dioxide from sulfur and oxygen, and the equation is S plus O2 equals SO2. SO2's enthalpy of formation is negative 297 kilojoules per mole. This means that to make 1 mole of SO2 in the equation, 297 kilojoules of heat are released. Notice that the delta H has a tiny circle right after it. This tiny circle means that the reaction occurred in standard conditions. So, under standard conditions, which is a temperature of 25 degrees Celsius and a pressure of 1 atmosphere, the reaction releases 297 kilojoules of heat. The heat of formation of individual elements is always 0 since they're already formed. For example, delta H of formation of N2 gas is 0 because it doesn't take or release any energy to form it. Sometimes you'll see a fraction as a coefficient for one of the component elements. For example, the reaction for the formation of 1 mole of S2O is 2S plus 1/2 O2 gives us S2O. In this case, to get 1 mole of the products, you only need half a mole of one of the reactants. But what do we use enthalpies of formation for? Well, you can calculate the delta H of a reaction by using this equation. The delta H of a reaction equals the sum of the formation enthalpies of the products minus the sum of the formation enthalpies of the reactants. Let's do an example problem. This problem gives us the enthalpies of formation for ethanol, which is C2H5OH, carbon dioxide, and water. And then it asks us to calculate the change in enthalpy for this reaction, which is the combustion of ethanol. So, to find the delta H for this reaction, we need to find the sum of the delta H's for the products and subtract the sum of the delta H's from the reactants. Let's start with the products, specifically CO2. CO2 has a heat of formation of negative 393.5 kilojoules per mole. There are 2 moles of CO2, so we multiply this by 2. Negative 393.5 times 2 equals negative 787 kilojoules per mole. Remember that the heat of formation only gives you the energy used or released for 1 mole of a substance. So, if an equation has more than 1 mole of a substance, you multiply it by its coefficient in the reaction. Now on to the other product, which is liquid water. Liquid water has a heat of formation of negative 285.8 kilojoules per mole. Since there are 3 moles of water in the reaction, we multiply that by 3. Negative 285.8 times 3 gives us negative 856.5 kilojoules per mole. Now let's find the sum of heat of formations for the products. Negative 856.5 minus 787 equals negative 1643.5 kilojoules. Now we're going to find the sum of the heat of formations for the reactants. The heat of formation is for ethanol is negative 277.7, and there's only 1 mole of ethanol. Because oxygen gas is an individual element, its heat of formation is 0. So the sum of heat of formation for the reactants is negative 277.7. Let's take the heat of formation of the reactants and subtract it from the heat of formation of the products. Negative 1643.5 minus negative 277.7 gives us negative 1,365.8 kilojoules per mole of reaction. Let's do another example problem. This question gives us a reaction. CO plus 3H2 gives us CH4 and H2O gas, as well as the delta H for the reaction and the enthalpies of formation of CO and H2O gas. The question asks us to find the enthalpy of formation for CH4. So we know that the delta H of the reaction, which is given here, is equal to the delta H of the formation of the products minus the delta H of the formation of the reactants. CH4 is one of the products of the reaction, so we can do some algebra and figure out its heat of formation. First, let's find the heat of formation of the products, starting with water. The enthalpy of formation of water as a gas is negative 241.8 kilojoules per mole. And since there's only 1 mole of water in the reaction, we don't really need to multiply it by anything. As for the enthalpy of formation of CH4, we don't know what it is yet, so we'll just call it X. This means that the sum of formation of the products is negative 241.8 plus X. Now, for the enthalpy of formation of the reactants. The enthalpy of formation for gaseous CO2 is negative 393.5. And since there's only 1 mole of CO2, we don't need to multiply by anything. As for the other reactant, hydrogen gas is an individual element, so its enthalpy of formation is 0. This means that the sum of delta H for the formation of the products is negative 393.5. Now, let's plug these numbers into our overall equation. The enthalpy of reaction, which is given as negative 206.1 kilojoules per mole, is equal to the sum of delta H of the formation of products, which is negative 241.8 plus X, minus the sum of delta H for the formation of the reactants, which is negative 393.5. This gives us the overall equation of negative 206.1 equals negative 241.8 plus X plus 393.5. Subtracting 393.5 for both sides, we get that negative 599.6 equals negative 241.8 plus X. Adding 241.8 on both sides, we get that X equals negative 357.7. So the enthalpy of formation for CH4 is negative 357.7 kilojoules per mole. Finally, we're going to learn about Hess's law, which tells us that we can combine different reactions and manipulate them to make a new reaction. Using the delta H's for the separate reactions, we can find the delta H for the new combined reaction. Now, let's say that we have 2 separate reactions like these 2 over here. You can add these 2 reactions together to create a new reaction that looks something like this. This takes all the reactants from the 2 original reactions and puts them on one side. It also takes all the products from the 2 reactions and puts them on the other side. But how would you find the delta H for this new reaction? Well, it turns out that you can just add the 2 delta H's from the original equations together. The first reaction has a delta H of negative 116 kilojoules per mole, and the second had a delta H of 183 kilojoules per mole. So, in this combined reaction, the delta H is 67 kilojoules per mole, which is just these 2 added together. Now, what happens to the delta H when you decide to reverse one of the original reactions before adding them together? Well, then you would have to change the sign for that original reaction, and then you would add the 2 together. So if I decide to reverse the first reaction and add it to the second reaction, I get a new reaction that looks like this. To find the delta H for this new reaction, I would change the first reaction's delta H from negative to positive before adding it to the second delta H. Positive 116 plus positive 183 gives us an overall delta H of 299 kilojoules per mole. There's one other thing you can do to the original equations, and that's multiplying a whole equation by a number. And when you do that, you multiply the delta H by that same number. So, with these two original equations, let's say that I want to triple this first equation. That would give me this reaction right here, and I could add it to the second reaction to give me this brand new one. To find the delta H for this new reaction, I would first multiply the original reaction's delta H by 3, since we tripled it, and add it to the second one. Negative 116 times 3 plus 183 gives us a new delta H of negative 165 kilojoules per mole. Now, let's review what happens in Hess's law. When you add two reactions together, you add their delta H's. When you reverse a reaction before adding it, you reverse its delta H by flipping the sign. Finally, when you multiply a reaction before adding it, you multiply its delta H by the same number. Let's try another problem with Hess's law. And unlike the other questions in the video, I did not create this problem. And this problem was from the website chemteam.info. This problem tells us to calculate the delta H for this reaction with the reactions below. Let's look at this reaction over here. We can see that the combined equation has 1 mole of solid carbon on the reactant side, and the only equation with solid carbon is this third one. However, in this equation, there are 2 moles of solid carbon, and they're on the product side. So we need to reverse this reaction to get solid carbon on the reactant side, and half the reaction to get 1 mole of solid carbon. This means that we need to flip the sign for this reaction and multiply it by 1/2. Negative 1/2 times 2,440 gives us a delta H of negative 1,220. For O2, the other reactant in this combined equation, we can see that O2 is present in 2 equations, so let's not worry about it right now. For the product, CO2, we see that the only reaction with CO2 in it is this first one. However, the first reaction has CO2 on the reactant side, and the combined reaction has CO2 on the product side, so we need to flip the first reaction around. This means that we change the sign for delta H in this first reaction from negative to positive, giving us a new delta H of positive 234. And the moles of CO2 are the same in both reactions, so we don't really have to worry about that. Now, let's add the 2 modified equations we've made and see where we need to go from there. For this third reaction, we reversed it and multiplied it by 1/2, so its new equation will look something like this. 3/2 O2 plus 1C plus 1 SR gives us 1 strontium 2 carbonate. And for this first reaction, we reversed it, so it'll look something like this. SrCO3 gives us strontium 2 oxide and CO2. Adding these 2 new reactions, we get Sr plus C plus 3/2 O2 gives us SrO plus CO2. I got rid of the SrCO3s because the same moles of SrCO3s were present on both sides of the equation. Now, how do we get from this equation to the final one at the end? Well, I noted that we need to get rid of the SrO to get to the final equation. We can get rid of the SrO in the products by adding some on the reactant side so they cancel out. In the second equation, which we haven't used yet, there are 2 moles of SrO on the reactant side. To cancel out 1 mole of SrO on the product side, we need to multiply the second reaction by 1/2. Multiplying the delta H of the second reaction, 1,184, times 1/2 gives us 592. Now, let's write out this halved equation and add it to the one that we made earlier. The halved equation number 2 is SrO gives us Sr and 1/2 a mole of O2. Now, let's add it to the equation that we wrote earlier. We can get rid of the SrO and the Sr since it's on both sides of the equation, and we can subtract 1/2 mole of O2 from both sides, so there's only 1 mole of O2 in the reactants. This gives us 1C plus 1O gives us CO2, which is exactly how we got this final equation. Now, to find the delta H for this final equation, let's take all the new delta H's we've got and add them together. Negative 1,220 kilojoules plus 234 kilojoules plus 592 kilojoules gives us a final delta H of negative 394 kilojoules. And guess what? You've made it to the end of AP Chem Unit 6. Thank you guys so much for watching, and I'll be sure to see you all in Unit 7, which is all about equilibrium. Bye!